Good morning.
Yeah.
Every hackerspace has a wish that you could make your very own PCB. And wait no longer, because Jeff here is going to make that happen today. And I would say, Jeff, take the floor away and make it rock.
Thank you. Okay, hi everyone. My name's Jeff. I'm going to introduce a new printing machine for printing circuit boards. So what is a PCB? It's a printed circuit board. It really has two functions. So this is a really close, zoomed-in shot of a circuit board. They're usually those flat green objects you get in your PC or whatever. Your motherboard is an example. It's a flat sheet of fiberglass, and then on top of that, there's a patterned layer of copper, which here is actually green, because on top of the copper is a layer of stuff called solder mask, which is a protective coating that stops solder spreading too far. And on top of that are the components. So the PCB gives you two things. It gives you a mechanical support that holds all of your electronic components physically in place, and it also provides the electrical connectivity between your components. So if we cut through the circuit board, you can see all of the different elements. So in the middle, there's the fiberglass layer. That's the real mechanical strength of the thing. On the top and the bottom are the two patterned layers of copper. Around the place, here and there, are these things called vias, which are connections between the top and bottom layers that go through the board. And they are a hole that's been drilled through the board, so it's a cylindrical hole, and then there's a layer of metal deposited around the inside of that hole that establishes a connection between the top and the bottom. On top of all of that are your components. So this might be a chip or something, and then legs come out of the components, sit on the copper, and then they're soldered in place. And finally, this green material is that solder mask I was telling you about. So this is the protective layer that stops the copper from oxidizing or getting corroded by crud in the environment, and also stops solder from flowing too far when it melts in the manufacturing process. So why would you want to make your own PCBs? Here are some of the alternatives to a PCB. Oh my goodness. Yeah, there are no nice ways of prototyping your electronics. So a circuit board is really the only way. I mean, the whole of industry has optimized all of the designs of the electronic components that you'll want to use for mounting on a circuit board. And everything else is kind of a bit of a poor imitation. So why not use an Arduino? I've been sort of subtly berating the Arduino in all of my marketing merchandise, and I really have nothing against it. I think it's a great way to get into electronics, and it's been great for sort of artists and people who have no electronic experience. But the thing about an Arduino and any other sort of pre-built electronic module, the Arduino, of course, is itself a PCB with components soldered on, is that it's not as flexible as you might want. So at some point, as you get more experience with electronics, you'll want to maybe design something super miniature that you can't buy in an off-the-shelf module, or use a chip that's brand new and no one has modularized it for you yet. Or you might want to design some analog circuit which is specific to a particular job and just isn't available in an off-the-shelf, pre-assembled piece. But why would you want to make your own when you can get a PCB from a quick turnaround prototyping service in about 3 days for about 50 euros? And this is pretty much true across Europe and America, certainly, and cheaper, but also a little bit slower if you outsource to China. I think there are two reasons. It's not fast enough, and it's not cheap enough. If you've got a quick idea and you just want to try it out in a kind of sketch, then you don't really want to wait 3 days on the whole. And also, when you're prototyping, I think the real problem with prototyping on breadboards and all of those horrible things that I showed you is that, whilst they are sort of unpleasant and tend to be quite unreliable, I think the real problem is that as you prototype, you get no closer to your finished object. Although your circuit design is converging upon your finished solution, you're still going to need to transcribe that from a sort of breadboard layout or a strip board layout or something into a finished PCB. Whereas if you can quickly iterate through multiple PCB revisions, you'll gradually close in on your finished product, and then your final prototype will essentially be your finished PCB. So how are PCBs made industrially? Let's look at that. Again, this is a series of cross-section views through the PCB as it's developing through the manufacturing process. So you start off with this laminate of the fiberglass and a thin layer of copper on the top and bottom. Next, the holes are drilled through to establish the places where components with legs are going to end up, for example, connectors and stuff. Increasingly rare these days as people are moving towards surface mount stuff. But also, crucially, the vias which establish the connections between the top and the bottom. Next, photoresist is deposited, and this is a light-sensitive polymer. Then the masks, which contain the image data for the top and bottom of your design, are placed on top of the photoresist and exposed to UV light. And the areas which are exposed are chemically changed and become resilient, and the areas that are hidden by pieces of the mask are not. And here you can see that patterning of the chemically changed regions and the unchanged regions. And then you put it into some magical chemical, and that dissolves the unchanged regions, leaving in place the hardened areas that have been exposed to the UV. So at this point, there is the image data in a 2D protective plastic layer, basically, on top of the copper, and some exposed regions of copper. Next is placed into a series of even more magical chemicals, which deposit a thin layer of slightly conductive material on all of the insides of the holes. And now the whole assembly is electroplated, and so that thin layer of copper is grown up to a much thicker layer, and the slightly conductive bits through the holes are grown out into a properly conductive piece of bulk copper that establishes that electrical contact. Then a layer of tin or another more inert metal is plated on top of the copper. And the photoresist that was hardened is stripped away. So you've now got your patterned copper image on the top and the bottom, protected by tin plates, and the thin layers of copper that were just there to establish the electrical connections for the electroplating process are then etched away. So at this point, there's the finished electrical component of the design. The top and the bottom layers of copper are patterned, and they're ready for use. And now the solder mask is applied. So to start with, solder mask is applied to the whole PCB, completely covering everything. And there's another masking step that happens. So this solder mask is that green protective layer that I mentioned earlier. It's imaged in the same way as the copper, essentially, or the photoresist, rather. 2 more masks, which now contain the image data for the solder mask layer, are placed on the board, and it's exposed to UV light, again, and that chemically changes some regions of the solder mask. And now a different solder mask-specific developing chemical strips off the areas you don't want. So for example, the areas where you're going to solder a component's legs onto the board, they obviously don't want a protective plastic layer, they need to be exposed copper. There'll be windows in your solder mask. So yeah, so that's sort of 16 basic steps, and of course that's the abridged version. So there's a whole series of cleaning steps probably for each of those major steps, and I also just sort of conveniently introduced these masks. Where did they come from? They themselves are the output of another photolithographic imaging process themselves. So how is it done by hackers? Obviously, replicating all of those 16 steps, whilst possible, and has been done by hackers in their hackerspaces and in their basements and whatever, you really want to pare that down. And I think there are two fundamental steps. The first one is producing that etch-resistant patterned layer of protective plastic, let's say, or any other material that's going to resist the sort of acid bath that etches the copper. And then the second step is etching the copper itself. So that's a chemical bath which eats away the exposed copper and hopefully won't eat away the protective layer that you've deposited. So the most stupid way you could come up with of creating a protective layer is just with a marker pen and physically draw it on your board. But obviously, you're not going to be able to produce very fine detail of the sort that you really want in a circuit board. And if you make a single mistake, you have to draw the entire thing again. And yeah, you end up with stuff that looks like this. So it's kind of, it's obviously a PCB layout, and it probably works, but it's not particularly pretty and not particularly repeatable. So option 2. This seems to be increasingly popular at the moment. A lot of hackers are doing this. Toner transfer. So you print out your design on a laser printer onto shiny paper, and then you rough up the surface of your copper board so that it's nice and easy to stick things to. And then you place your toner out of the printer face down onto the copper and heat it with a household domestic iron, and that melts the toner, which is essentially black plastic, onto the copper. And then you soak off the paper and clean off the paper residue and stuff, and you're left with this resist. So step 1 is accomplished here. You've got this patterned area of plastic, toner, stuck to the copper, and that looks like a really nice result there. And then the easy step, step 2, chuck it into a bath of etched chemical, and that eats the exposed copper, and you strip off the toner and you have your finished PCB. Option 3, photolithography. So a bit like the industrial process, but with a few steps removed. You can buy PCB material that comes coated in photoresist already, and people make their own UV exposure boxes, print out their artwork on maybe transparency film with a printer, inkjet or laser or whatever, and then expose it to light, develop it, and etch it. So another option, option 4 maybe, isolation milling. So I meant to draw your attention to the number of steps in each of these processes. So, this kind of appears on paper to be pretty much the best option. There's just one step. You put the PCB in the machine and you mill it out. And this is a mechanical cutter that's eating away areas of the copper that you don't want. But unfortunately, the process really sucks. It's really difficult to avoid getting kind of burrs and chewed up areas of the copper that are going to cause problems later on. And also, you're never going to be able to get close to the resolutions that a kind of chemical or optical etching process are going to produce. So although it's incredibly simple, it's also quite limited. Another option, I've only seen a couple of people do this. This guy modified a pen plotting machine to move around an optical fiber that's coupled to a UV LED, and then he uses that to expose photoresist-coated PCB, and then he develops it and etches it. So that's pretty much a 3-step process, and pretty cool, but really slow because probably the output power of the LED is limited, but he has to plot the tracks very slowly to sufficiently expose the photoresist to the UV. Another option, lots of hackers and hackerspaces now own laser cutters, and people are playing around with using laser cutters to etch PCBs. Now, you can't etch the copper directly with the kind of laser that you can afford to buy yourself, or as a hackerspace even, because you just don't have enough power to erode the copper. It just wicks away the heat too quickly. So people paint on black spray paint and then etch that off with the laser. And then they clean off the board because it leaves a kind of ashy residue, and then etch it. Another option, inkjet technology. So people take an off-the-shelf inkjet printer. Usually they have to modify it to use a more water-resistant ink, because obviously the etch solutions are all water-based, and if you have water-based ink, the etch is going to dissolve the ink as well as the copper. So people use more water-resistant inks, and then there's also a step of baking the ink to get it to really sort of solidify onto the PCB itself. So it's not quite as simple as it might appear, just printing and etching, but it's definitely getting close. So at this point, I should probably just cut to a part of the demo side. So my demo's not working 100%, and I'll explain why a bit later on. But I have here a PCB that we printed earlier, which just contains a couple of lines. Now, you won't be able to see it, but we'll show you on the camera in a second. So this is just to demonstrate the etching part of the process. So remember, there's two steps, the printing part and the etching part. So you want to come up, Rob? And if we can switch to the video, that would be great. Okay, cool. So I don't know if you can see this. This is the PCB that we've printed, and you can just see at the top here there's a couple of lines. One's a little bit fuzzy, one's nice and crisp. And there's a few little splashes of wax and stuff around, and I'll explain all of this later, but I have to get it in at this point because it takes about 20 minutes or so to etch. Yeah, so these two lines that are in wax at the moment are the important bits. Sorry, at the top here, this one and this one. Hopefully they will be revealed at the end. So here's the etch solution. We've got this nice insulated bento box here, which is going to keep the etch nice and warm. The speed of the etch is pretty much just dependent on its temperature. So this is about sort of 40, 50 degrees. And we'll just chuck the PCB in. And Rob here is going to look after the etch process, and we'll show you what it looks like at the end. So yeah, it's nice and simple. We just chuck it in the solution and then occasionally sort of swill it around. Thank you. So we'll switch back to the slides now, if possible. Okay, so that is the inkjet method that some people are using. I'm going to try and do a bit better than that and introduce my process, which is based on inkjet technology, but with a key change. So instead of using an off-the-shelf ink or one of these special extra waterproof inks, I want to use wax. So I'm going to print liquid molten wax. And the wax is a liquid in the print head, and then it comes out and it hits the cold copper surface and freezes immediately. One of the main problems with the inkjet process, which I forgot to mention on the previous slide, is that the ink tends to accumulate into a fairly large mass and then form big droplets and kind of draw together rather than maintaining that perfect image that you're aiming for. But my hope is that by printing liquid wax, it's liquid, hits the PCB, freezes solid, and it's not going to spread. It's also obviously waterproof rather, so it should be pretty resilient against the etch. And unlike inkjet inks, it doesn't contain any solid particles which might block up the print head over time. So inkjet inks are designed on this absolute knife edge. They absolutely mustn't dry out, because if they dry out, the solvent evaporates, leaves a solid residue in the print head, and gums up your printer. But also, they have to dry instantly, because when they hit the page, you want them to dry before they spread and blur out your image. So this sort of knife edge of design is obviously a major problem, and it's something that we can completely avoid by using wax, because we don't care about it containing any dye. We're not aiming to produce a pretty photograph. Finally, you're not reliant on a manufacturer's ink recipe. So if you go to the shop and buy Epson's Super Glossy Ultra Pro Ink 2000 this week, and then you print it and you make a PCB, maybe next week the stuff that you buy might not necessarily be the same. It might be as good for printing photographs, or even better maybe, but it might not have the same PCB properties because it hasn't been designed for that. So can you actually do this? Can you inkjet print wax? And the answer is yes. There's a while ago I had this crazy project where I had to make this pair of shoes covered in LEDs in no time. And there just wasn't time to outsource the production of flexible circuits to coat these trainers with. So I bought this machine, which is called a Xerox phaser printer. And it inside contains an inkjet printer that prints liquid wax, molten wax, onto a drum, and then it rolls the drum onto the page. And I just took flexible PCB laminate, which is very much like the laminate I introduced at the beginning of the industrial process. It's a plastic with a thin layer of copper on top. I just cut it up into A4 sheets, loaded it into the printer, clicked print, and it came out with perfect wax image on perfectly clean copper, and then I etched it and soldered it and ended up with this PCB, and it was incredibly simple. So we know that, one, you can inkjet print wax. This is doable because you can buy a machine that does it. And two, wax is an effective etch resist. So I'd like to produce a machine that's kind of like the MakerBot of PCBs, I suppose, to try and just simplify this process and democratize it. So here are my goals. 2 steps: print, etch. No dicking around, no sanding of PCBs, no cleaning, just 2 steps. Feature sizes smaller than 0.2 millimeters, which is the low end of industrial processes. I think this project is useless if you can't match at least some of the capability of industry, because then your designs can be carried both ways from the mass-produced world into the hacker world and vice versa, if you can keep the same design rules, essentially. I'd also like to be able to print on both sides and align them, index them together. But I should point out that I have no solution yet for connections through the board, those vias that I mentioned earlier. So yeah, that's one for the community. If you've got any ideas, that would be great. So let's choose a print head to use. That's really the heart of the inkjet printer, the device which sucks in ink from a tank and squirts it out onto a surface in a really accurate way. So there's 2 types of inkjet technology. One is the piezoelectric type. So here there's your ink tank, your ink cartridge, and then there's a system of plumbing, basically, that carries the ink up to the nozzle. On the top of the nozzle is a thin diaphragm of stainless steel or silicon, and on top of that, the piezoelectric element. And a voltage is applied to the piezo, and it bends upwards, and it does this slowly to draw in ink from the reservoir, and then it sharply accelerates downwards with an opposite voltage pulse, and that expels a droplet of ink. And the other method is the thermal method. So very similar plumbing, but instead of that piezoelectric membrane, there's a heater, and the heater quickly dumps energy into the ink. It vaporizes, and under the pressure of its own vapor, it expels a droplet. I want to use the piezo method because the thermal method has a very short lifetime. These power resistors essentially have such high currents pumped through them that they age very rapidly. And this is why everyone in the consumer market except Epson use this technology. And they sell their printhead as part of the cartridge, whereas Epson sell a piezoelectric printhead which is part of the machine because it's got that longer lifetime. So I'd like to use the piezoelectric method because longer lifetime, and also you get a little bit more control over the ink formulation. You don't have to have something that's easily vaporized and all of that. So yeah, I use pretty much the crappiest, cheapest printer you can buy. This is really the bottom of the range. This prints 4 picoliter droplets, which are 19 microns in diameter. That's about the diameter of that's about a third of the diameter of your hair. And on the nozzle plate, there are 30, 30, and 30 nozzles of cyan, magenta, and yellow, and then a 90 nozzle strip of black. And obviously, by having more nozzles, you can print more at once and sort of parallelize the process and speed it up. And you get all of that for 40 euros, which is absolutely insane. So if you strip apart all of the bits of printer that you're not interested in, you get to this print head. So here are the 4 needles that plug into the 4 cartridges, cyan, magenta, yellow, and black. And on the bottom, the bit we're really interested in, this nozzle plate, the assembly of microfluidics and piezoelectric gubbins and wizardry that actually does the printing. If you take that out, you can see what it looks like. There's the nozzle plate itself that's got 2 rows of nozzles that are barely visible and certainly not visible in this photo. And then on this flexible circuit board in the middle, that little black blob is the control chip. And that is what we're interested in talking to. And I'll talk about the reverse engineering of that in the coming slides. Flip it over, and you can see the 4 ports which allow ink into the print head. So that's cyan, magenta, yellow, and the one on its own here is the black one. And they connect to the system of vessels that leads up to the ink cartridges. This PCB on the left is purely a connector. It's completely done. There's no electronics on there. The only electronics we're interested in, again, is that black blob in the middle. I meant to delete this slide. This is an inside view under a microscope, and the nozzles are hilariously small. You can see that row of nozzles there. But it's kind of a bit of a crappy image. So now we need to obviously heat up this whole print head, and we can't heat up the whole plastic assembly of tiny plastic tubes because plastic's such a good insulator that wax is going to freeze in the tubes. So I started machining this sort of printhead reservoir block to replace all of that plastic gubbins. So there's the 4 holes with the 4 colors of ink, although probably I'm only going to use one ever. So the ink goes in at the top, and then it comes out the bottom in these 4 smaller holes here around the edges of this piece, which are coupled onto the printhead itself. To supply the heat, there's a power transistor at the top right, which is essentially just shorted out. Oops. And then on the other side is a temperature sensor that measures the temperature, so we can control the temperature by delivering current to the power transistor and measuring the temperature rise on the heater. And yeah, that works. So now we're looking at the bottom of the print head, and you can see that heater, the transistor, and the temperature sensor, and there's a droplet of liquid wax dribbling out. So that part is sorted, at least, the easy bit. So we've got this heated block, and we've got to couple that onto Epson's print head, and you've got this aluminium block with 4 holes and this print head with 4 holes, and you've got to make them together. And this is not easy. I came up with this really elegant solution, and I was really proud of myself. I took double-sided sticky tape and then laser cut it into these little precision gaskets, and then stuck these gaskets on the back of the print head so they just expose the 4 holes, and then you bond it onto the print head. But it really sucks. It's really leaky, and not very much of the wax actually ends up where you want it in the print head. So then I thought I'd do what Epson do. They deposit a liquid gasket of silicone rubber, and then that seals and cures and forms a watertight layer. So I made this stencil on the laser cutter. This is just a thin plastic membrane, and you can see there's a big blob of silicone at the top there. Squeegee the silicone over the stencil, peel off the stencil, and you've got these 2 precision islands of shaped silicone liquid, and then glue the print head on top. Whoa, what's going on there? Oh dear. Spoiler. Oh my goodness. Hang on. Sorry. Hang on. Yeah, sorry about that. Yep, gaskets, yeah. But this still sucked because the silicone I used was an air-curing silicone, and once you've assembled this contraption, there's no air left. And so the silicone never really set, and it could never withstand the pressures that I needed to prime the nozzles the first time round. So third approach, laser cut rubber gasket made out of bicycle inner tube, and then mechanically clamp the print head down onto the rubber gasket. And that still really sucks, but it just about kind of works. It's still incredibly leaky, and I think that's the major reason why my demo today is incredibly sketchy. So yeah, if anyone's got any good ideas, I think really the solution is the silicone, but with two-part silicone, not air-curing silicone. Anyway, we've sorted out the plumbing, partially. How are we going to do the electrical interface to actually control this thing? Now, this is obviously a reverse engineering task, because Epson aren't just going to tell you how their print heads work. So the first bit of any reverse engineering task is to read around to see how much you can get away with not doing yourself. And there's two previous reverse engineering attempts that I found of Epson technology. One, a guy called Volkan Sahin, who reverse engineered a much older Epson head a few years back and used it to print a particular type of ink for PCB construction, actually. And he's got a few details on his website, but they're a bit vague, and he's a bit shady about it. There's another project, really cool, called POSSAM, which is an academic project somewhere. A bunch of researchers reverse engineered an Epson print head and used it to print DNA arrays. So the next thing, patents. Patents are an excellent source of information, it turns out. Don't read any of the text. It's mostly this word, and is completely impenetrable. But some of the diagrams are quite good. And this is actually a pretty detailed description of the electrical interface, and it's just in the Epson patent. You can just download it and read it. And you can see the sort of key elements of the interface here. There's this analog magic voltage waveform that physically actuates the piezo membranes, and then there's this digital interface at the bottom that clocks in the data. So this is a sort of system overview of the print head. There's that magic square wave voltage pulse there that actuates the piezos, and then that is connected to the various nozzles with this multiplexer chip. That was the little black blob in the flexible PCB that I showed you earlier. And you shift in the data on this digital bus here, and that basically sets some switches, and then depending on which switches are pressed, when you give it that voltage spike, some of the nozzles fire and your image data comes out. Okay, I used this thing to start reverse engineering the digital interface. This is the OpenBench Logic Sniffer, which you can buy for about 40 euros or something. And I interposed that between the printer with its default Epson motherboard and everything, and the print head itself. So I've sort of spliced it in the middle here, and I'm watching the data go by between the printer and the print head. And there's a decent amount of information in the patent about the structure of that data, but I had no idea which physical pins on the device corresponded to which signal. And so by attaching the logic analyzer and looking at the shape of the traces and reading the patent, I was able to work that out. So then I built my own board here. I didn't print this myself. Obviously, there's a bit of a chicken and egg problem, so I outsourced this. This contains the digital to analog converter for producing that magic trapezium-shaped wave pulse, and also this digital bus which connects to the printhead, and you can see the printhead up at the top there. There's also this development board off at the left, which is doing the PID temperature control of the nozzles and it's of the printhead block rather, and it's keeping that at a flat 70 degrees, give or take. So here's the magic waveform coming out of my device. I basically copied all of the timing off the Epson hardware by just looking at it on an oscilloscope. And these are quite rapid. So this sharp rise here, the one that actually does the sort of physical expulsion of ink, is about a microsecond, or probably much less than a microsecond actually, the rise time. So it's quite a high-speed situation. And it works, which is pretty cool. So here we're looking at the bottom of the nozzle plate, and these wisps are streams of wax droplets. And I'm just cycling through one nozzle after another. And so there, this is a cloud of, each pulse is a cloud of 1,000, I think, wax droplets coming out of the print head. So here's the complete assembly, and the thing I've brought with me today. You can see the mechanical assembly is scavenged from an even older Epson printer rather. That's a bit easier to play with because it's got stepper motors and things rather than servos. There's my couple of development boards mounted on here, and you can just see the print head up at the top right mounted on the carriage, and that goes back and forth and does the printing. So, results. This is a Lego brick. I didn't print this. You've probably seen these before, but the little blob on the top is about 3 millimeters in diameter, and we're looking at this down a microscope. And if we just switch the focus slightly, you can see that on the copper plate below, there's some very fine tracks here. So these are little tiny stacks of wax droplets. So it's quite high resolution. Also, you can do 3D. You can just stack up droplets on top of each other, basically. So, so these are stacks of about 1,000 droplets each. And this is one of these stacks really close up in this insane focus stacked image. So this is a composite of lots of different images taken at different focal lengths. And you can see that it's like an icicle. It's obviously one complete piece of wax. And you can see it's got this kind of blobby look to it. But those blobs aren't individual droplets. They're actually sort of just a kind of freezing zone, I think. And these hairs coming out the side here are kind of on a closer scale to the size of the droplets. So they really are tiny. And there's potential for some pretty high-res 3D printing of stuff. But we're not interested in 3D for now. We want to do 2D circuits. So I started trying to print a large patch of copper, of wax rather, and then etch it into copper. So here's a patch. This is essentially a load of lines printed right next to each other, really, really dense. And I etched them, and I was really surprised they actually came out almost as individual lines. I was hoping that they'd just agglomerate into a single mass, but the resolution was sufficiently high that they almost came out on their own. So I think these lines are about 0.1, no, probably less, about 0.05 millimeters wide. This patch on the top right of this PCB is what I was aiming for, so I reduced the spacing between the lines and printed thicker wax and stuff. So I got this solid patch, which I was really happy with because it proves that you can actually make a thick, nice etch-resistant layer that's going to be able to print ground planes and stuff on your PCB. And there's a single pinhole defect in the middle that's actually massive, but other than that, it's just a perfectly solid plane. So, raster images, that's what we really want, right? Just about see this raster image emerging from the machine, one line at a time. I'm only using a single nozzle at the moment because of a variety of problems. So it's really, really slow, but it certainly works. There you go, there's the finished image. And etch it in the bath. And you end up with a patterned board. Now this is a little bit crappy. There's lots and lots of pinhole defects in here, and so it's really not very good as a circuit board. So then I changed the settings a bit and produced a thicker layer and stuff, and this is actually pretty perfect. There are very few pinhole defects in this. This is the second attempt at a raster image. So then I started to try and push the resolution, see what kind of features I can create, and they're getting pretty dense. So what's next? Better priming of the wax nozzles is what I want, because at the moment nozzles only print for a short while and then end up failing. And I think that's not, catastrophically failing forever, but they accumulate a layer of wax on the print head itself, and that prevents droplets from leaving, and they essentially just kind of stack up in this growing blob of wax. And there's probably about 1 million factors that go into this, but that's the key problem that I need to solve next. And I think the real problem that's causing insufficient priming is this crappy seal between the print head and the reservoir block. Suggestions on a postcard. There's still some craziness in the digital interface with the print head that I haven't quite got nailed yet. There are some nozzles which spuriously fire when I'm not expecting them to. And there's also, in the printhead interface, there's a kind of grayscale feature where each individual pixel is composed of several sub-pixels. And I don't really understand how that works, and that's been the cause of several strange interfacing problems. But hopefully I'll get that nailed by reading some more patents and digging out the logic analyzer again. Now, even Epson have problems with wax, or rather ink, accumulating on the nozzle plates, so they actually have a squeegee blade mounted in the printer. So your nozzle scans up and down for a bit, and it prints your image, and then it stops, moves over the squeegee, squeegees itself, moves over this thing called the spittoon, which I think is a hilarious name, and it purges ink into the spittoon for a while to clear out all of the nozzles, and then it squeegees itself some more, and then it goes back to printing. So you might have noticed that with your sort of So I need to do that bit, the stage. So yeah, 3D would be something I'd really like to do. So this is I didn't print this, obviously. This is a commercial 3D inkjet-based wax printing machine used in the jewelry industry for making wax-positive molds that are then cast into physical metal objects. And yeah, resolution is completely nuts. And actually, the droplet size of this printer is much, much larger than the droplet size of my printer, which, well, is kind of actually a problem because I don't want super high-resolution droplets. I just want it to work at the moment. So it would be much easier if these nozzles were a little bit bigger and a little bit friendlier. But anyway, even with bigger nozzles, you can achieve completely insane 3D resolutions. So yeah, I'm going to show you around the printer now. Unfortunately, I haven't got it printing because of this crazy plumbing situation. But hopefully, we've got some lines on a PCB. Rob's just taken it out of the etch solution now. And I guess if anyone has any questions, you can start sort of thinking about them and chipping them in. So can we switch to the video, please? The camera. Yeah, here we go, cool. So, okay, so this has come out of a... Can I focus on that? Or should I put it on the table? I'll try not to jiggle too much. Yeah, so there's two lines there, which is pretty cool. Try and see if I can get the light on them there. Yeah, there we go, lines. Excellent. Thank you, Rob, for your etching help. And I'm going to show you around the printer as well, just a little bit. So, thank you. Get the crap out of the way. So yeah, so we've got the print head here, and you can move that up and down on the axis. That's Stephan motor controlled. And if I take this piece out, this is the print head assembly. So on the bottom here, you can see this. This is the nozzle plate, and if I try not to jiggle too much, you might even see. Nearer. Sorry. Yeah, there you go. You can see two rows of nozzles there, and just over here you can see lots of nice accumulated wax goo, which is the problem of the day. So yeah, you can see the two rows of nozzles. So that's 80 black nozzles in a line. No, sorry, 90 black nozzles in a line, and 87 odd color nozzles. And then on the other side, you can see the port switch, lots of reservoirs that store the wax, and then there's the heater board there. Yeah. So that's pretty much it. And then there's just the control electronics down here and the heater electronics there. Cool. So has anyone got any questions?
If you have any questions, could you please come up to the microphone? And only ask the question in the microphone, please.
Thank you.
Go ahead.
Is it working? No? Yes? Ah. Hello, my name is Axel Roest. Thank you for a nice presentation. Is there a secret formula for liquidizing the wax? Because I think wax is normally solid. Like in the Xerox printers, there are solid blocks. Do you use solid blocks? Or
Yeah, just solid wax,
so
and
you
then
just melt it?
Just melt it, yeah, simple as that. I'm actually using wax from a craft shop that was sold for making candles, which is a terrible mistake. I should be using some wax supplied by, Sigma Aldrich or something that's got an exactly known chemical formula rather than just like super glossy candle wax. But yeah, literally just a block of raw wax without any special additives.
I have one more question, sorry. Wax is like melts in heat. That's what you use. But you also most etching things are used with a heated solution, like 50 degrees, like that box over there. Doesn't the wax melt in your etching solution?
That's a good question. Yes, the answer is yes. If you turn up the solution of the temperature of the solution too high, then the wax melts. This wax melts at about 65 degrees Celsius, and it's being printed at 70 degrees Celsius. And the etch solution works, well, it says it works best at 50, although that's probably just a safety measure, and I suspect it works better and better and better the hotter and hotter and hotter you make it. So I'm etching at 50 degrees C, which is below the melting point of the wax.
Thank you.
Cheers.
Sir?
We've done some sealing with a two-component glue, so with Uhu Plus, and then if you put on a very, very thin layer of that, take care that you don't plug up the holes. Maybe that's worth a try. Of course, you only have one try. If you put them together, you never get them apart again. So perhaps you should think about that.
Yeah, definitely. Thank you. I think a two-part. Is that an epoxy or? Yeah.
So you have an epoxy and a hardener that you mix together and put it on there.
Yeah, great. Thank you. I think definitely a two-part thing is going to work better than the air curing stuff. Yeah.
One way you can look is motor sealing stuff. Like there's some black silicone which you can use to seal motors together, and they have stuff like that. Maybe look in that shops. Maybe find something you like.
Okay, right. Yeah, that's a very similar problem, right? Assembling cylinder heads onto engines. Yeah.
Did you look into any other printing media to achieve the same result, possibly without having to heat it first, such as waterproof marker, ink, or stuff like that?
Okay, so did I look at alternative inks? Basically, no. I'm really excited about printing wax because there's nothing to dry out and solidify and gum up the print heads pretty much. So I'm kind of scared of, because my printer lacks any kind of self-cleaning mechanisms and stuff, I'd really prefer to use an ink that is liquid and then is a solid, nothing that can dry out and clog up the print heads. And the other advantages obviously solvent-based inks would probably be better in this regard, but water-based inks are no use at all because the water-based etch is going to eat them. So, at the moment, no, but I just thought yesterday, actually, it might be fun to try and print immersion tinning solution. So this is a chemical which you place on copper and it deposits tin onto the copper. And tin is an excellent etch resist. But that is, again, a water-based solution, and so if the water dries out, then the tin chemical is going to crystallize into the print head. So, I'd rather stick with wax if I can, is the answer. Thank you.
Two final questions?
Okay, sure.
How long does all the reverse engineering take you? So it's not quite as easy as it seems. So how long did it take for the whole project?
Okay, good question. I suppose, to be fair, I haven't done a huge amount of reverse engineering. Because it's documented so well in the patents, I pretty much wrote some code based on what I'd seen in the patents, used the logic analyzer to work out which signals were which, and it more or less worked. I quite rapidly got to that video I showed you where the individual nozzles were being turned on and off. So, I didn't have to work nearly as hard as I was expecting, and I don't know, only a couple of days.
Sir?
Okay. How do you solve the problems with two-sided printing? So
those problems aren't
mechanical
solved.
Stuff.
Good question. Lining up two layers is obviously tricky, but I can imagine, maybe drilling some holes through, and then you've got an index, and then either lining that up with some mechanical fixture, or maybe one day a kind of gantry with computer vision would be absolutely awesome. But Yeah, I haven't really tried. I've been mostly concentrating on the sort of fundamentals of getting a wax image onto a copper surface so far. It doesn't seem to be too difficult. The real challenge is electrically connecting the two layers. That's the killer feature. Yeah, and I don't have a solution for that.
Thank you.
Thank you.
Will you make your findings available for all the hackerspaces that are around?
Yes, absolutely. I actually forgot. I was going to stick on this slide my website, warrantyvoidifremoved.com.
Give him a round of applause. Thank you so much.
Thank you. I have one more thing to add. I'm going to take this down to the Hack Center now and just hang out there. So if anyone wants to come and play with it or whatever, I'll be down there. Thank you.
Thank you so much.